February 16, 1943. The screwdriver quivered slightly in Ober-Engineer Klaus Hermann's hand as he opened the sealed metal casing of the captured American radio set. Around him, 5 of Germany's top radio engineers leaned forward, eager to inspect the equipment that had fallen into their possession during the recent engagement at Kasserine Pass. For 3 years, Berlin had claimed that American technology was inferior, mass-produced junk created by a nation of shopkeepers and assembly line laborers. The reports from the Radio Intelligence Service asserted that American forces relied on outdated gear, primitive designs, and poorly trained operators. Yet something seemed off. Allied forces maintained constant communication across vast distances. Their fleets never lost contact. Their ground units coordinated with a precision suggesting technology far beyond the primitive radios German propaganda described. The case opened to reveal an SCR-508 radio set captured intact from an American M4 Sherman tank destroyed in the Tunisian mountains. What Hermann and his team uncovered over the next 72 hours would shatter every assumption German military planners held about American industrial capacity, technical sophistication, and the trajectory of the war. The mathematics of radio communications were about to reveal a truth more devastating than any battlefield loss. The systematic analysis of American equipment would expose not merely a technological gap, but an industrial chasm so vast that Germany's defeat was already inscribed in frequency crystals, automatic circuits, and mass production methods that the Reich could never replicate. The capture had begun on February 14, 1943, at Kasserine Pass. General Erwin Rommel's forces, in a desperate counterattack against inexperienced American troops, had achieved a tactical victory, pushing the U.S. Second Corps back 50 miles and destroying over 100 American tanks. Among the wreckage, German technical intelligence teams moved swiftly, searching for weapons, documents, and equipment that could reveal Allied capabilities. Hetman Friedrich Baer, commander of a signals intelligence detachment attached to the 21st Panzer Division, had standing orders to capture any American radio gear intact. In a crater east of the pass, his team found an abandoned Sherman tank, its turret blown off by a German 88mm gun, but its radio compartment miraculously undamaged. Inside, Baer discovered not one but 2 complete radio sets, the SCR-508, designed for tank-to-tank communication, and an SCR-510 receiver. Both were intact, with their crystals, cables, and even the technical manuals still secured in their mounting brackets. Baer immediately ordered the equipment transported to the nearest German technical facility, knowing that this discovery could provide invaluable intelligence about American communications capabilities. The radios arrived at Technical Testing Station 12 on February 16. The facility, hidden in an underground complex beneath Tunis, housed Germany's top radio engineers, men who had designed the Wehrmacht's own communication systems. Ober-Engineer Klaus Hermann, former chief designer at Telefunken, led the examination team. With him were specialists in frequency generation, circuit design, manufacturing methods, and signals intelligence. They began with an external inspection. The American radios were encased in heavy-gauge steel painted olive drab, with rubber gaskets protecting every seam and connector. Hermann noted in his first report that the construction quality exceeded anything he had seen in German military equipment. The cases were designed to endure water, dust, shock, and extreme temperatures that would destroy most German radios. But the real surprise came when the cases were opened. Inside, everything was standardized, modular, and designed for mass production. Every component matched the specifications documented in the accompanying manuals. No hand adjustments, no technician marks indicating individual tuning, no variations requiring skilled assembly. This was equipment designed to be produced in the millions by semi-skilled workers in factories scalable across a continent. Leighton Hans Schreiber, a specialist in frequency control, examined the crystal units determining the radio's operating frequencies. He had expected simple, inexpensive crystals, perhaps even salvaged civilian components. Instead, he discovered precision quartz crystal oscillators, each ground to tolerances measured in parts per million, hermetically sealed in metal holders, with specifications that would have required weeks of laboratory work in Germany. The SCR-508 contained 10 crystal-controlled channels. Each crystal was individually packaged, interchangeable, and marked with precise frequency specifications. Schreiber counted the crystals twice, unable to believe what he saw. In Germany, crystal-controlled radios were limited to high command units in aircraft, where the cost and scarcity of precision crystals could be justified. Here, in a standard American tank radio, 10 crystals were installed as casually as light bulbs. He carefully removed one crystal and examined it under magnification. The quartz was flawless, the electrodes perfectly aligned, the frequency precisely marked. This single crystal would have cost more than the entire German Fug-5 radio set in materials and labor. Yet the Americans were installing 10 of them in every tank radio, and they had already produced thousands of Sherman tanks. The team's initial inspection revealed even more disconcerting facts. The radio operated on frequency modulation, FM, rather than the amplitude modulation, AM, used in German radios. FM was theoretically superior, providing static-free communication and resistance to interference, but it required far more complex circuits and precise frequency control. German engineers had considered FM for military use but rejected it as too costly and intricate for field deployment. Yet here was an FM radio, mass-produced, installed in a tank driven by junior American soldiers. The circuit board revealed automatic frequency control, AFC, circuits that kept the radio locked on frequency without constant manual adjustment. German radios required operators to continuously retune to compensate for temperature shifts, component aging, and power variations. American radios seemed to tune themselves. Ober-engineer Hermann began drafting his first report to Wehrmacht High Command in Berlin. The words came slowly, each sentence contradicting years of propaganda and intelligence reports. He wrote that the captured American radio represented a level of industrial sophistication Germany could not match. The components were manufactured with precision that required specialized factories, trained workers, and quality control systems. That simply did not exist in the Reich. More disturbing still, the radio was clearly not a prototype or limited production model. Every aspect of its design screamed mass manufacturer. The Americans were building these radios by the thousands. Over the next 3 days, the team systematically tested every function of the captured radios. They connected the equipment to power supplies, antenna systems, and test instruments that filled the underground laboratory. What they discovered with each test deepened their growing sense of dread. The SCR 508's transmitter produced 25 watts of clean FM signal on any of 10 selectable channels. The switching mechanism that selected channels was elegant, reliable, and required no technical knowledge to operate. A tank commander simply rotated a knob to select a preset crystal, and the radio automatically switched frequencies, retuned its circuits, and maintained perfect transmission quality. In German radios, changing frequencies required a trained operator to manually adjust multiple controls, replace coils, and spend several minutes retuning the equipment. Range tests proved even more disturbing. Using a captured American whip antenna, the team established contact with a monitoring station 20 kilometers away. The FM signal came through clearly without the static fading and interference that plagued German AM communications. Even when they deliberately introduced electrical noise from a tank engine, the FM receiver's limiter circuit stripped away the interference, delivering clean audio that German operators could only dream about. Lieutenant Schreiber focused his examination on the crystal oscillator circuits. He traced every component, measured every voltage, and documented the design in meticulous detail. What he found confirmed his worst fears. The crystal control system was not just sophisticated. It was impossible to duplicate with German manufacturing capabilities. Each crystal oscillator required a precisely cut quartz plate, ground to specific dimensions measured in thousandth of a millimeter. The crystals were then mounted in evacuated or gas fill holders with electrode spacing controlled to tolerances that German factories could not achieve in mass production. Temperature compensation circuits maintained frequency stability across operating temperatures from -40 to +60 degrees Celsius. Schreiber calculated that producing 1 Crystal to American specifications would require approximately 40 hours of skilled technician time in German laboratories. The Americans had installed 10 such crystals in a single tank radio. With thousands of Sherman tanks already produced in similar radios in American Jeeps, trucks, and command vehicles, the Americans were producing millions of precision crystals annually. He asked the obvious question in his report. Where were the Americans getting enough trained technicians to produce millions of precision radio crystals? The answer, when it came from intelligence sources, was even more disturbing. The Americans were not using highly trained technicians. They had industrialized the entire process. New factories in cities with names like Chicago, Newark, and Fort Wayne employed thousands of semi-skilled workers, mostly women, operating specialized grinding machines that produced crystals automatically. Precision measurements were performed by optical comparators and frequency counters, not skilled technicians. Quality control was statistical with random samples tested rather than individual inspection. The Americans had transformed a laboratory art into an industrial process. The examination of the radio's receiver section revealed even more advanced technology. The super heterodyne circuit design was similar to German receivers, but the components were superior in every measurable way. Vacuum tubes were manufactured to tighter tolerances with characteristics precisely matched to circuit requirements. Capacitors and resistors had stability ratings that German components could not achieve. The entire receiver was designed for alignment by semi-skilled technicians using simple test equipment rather than requiring radio engineers with years of training. Most disturbing was the modular construction. Every major subsystem, transmitter, receiver, power supply, and control unit was a separate replaceable module. A tank crew could remove a failed unit and install a replacement in minutes without tools or technical knowledge. Damaged modules would be returned to depot facilities for repair or disposal. This approach required massive industrial capacity to produce spare modules. But it meant that American tanks maintained communications capability under conditions that would leave German vehicles radio silent for days while technicians performed field repairs. The team examined the technical manuals that accompanied the radios. These documents, printed on high-quality paper with clear diagrams and simple instructions, assumed that operators had minimal technical training. Operating procedures were reduced to numbered steps. Troubleshooting guides used decision trees that any soldier could follow. Maintenance instructions specified exact replacement intervals for components rather than relying on operator judgment. Herman realized that these manuals revealed as much about American industrial philosophy as the radios themselves. The Americans had accepted that frontline soldiers were not technicians. Rather than train every radio operator to understand electronics, they had designed equipment that any reasonably intelligent soldier could operate and maintain using simple procedures. This required more sophisticated equipment. But it solved the fundamental military problem of maintaining communications under combat conditions. German radios, in contrast, required skilled operators who understood radio theory, could perform field repairs, and possessed the technical judgment to keep temperamental equipment functioning. These operators required months of training and years of experience. They were irreplaceable assets, and when they were killed or wounded, their equipment often became useless to whoever inherited it. By the end of the third day, the examination team had documented every circuit, measured every component, and tested every function of the captured American radios. Their report to Wehrmacht High Command was over 200 pages of technical analysis supported by photographs, circuit diagrams, and component specifications. The conclusions were devastating. The Americans possessed radio technology that was 5 to 10 years ahead of German equipment in key areas. Frequency modulation, crystal control, automatic frequency circuits, and modular construction represented fundamental advantages that could not be overcome by superior tactics or operator skill. More critically, American radio equipment was designed from the start for mass production. Every aspect of the design reflected an industrial philosophy that Germany simply did not possess. Herman's report estimated that Germany would need to build 30 new specialized factories, train 50,000 additional workers, and invest resources equivalent to the entire annual Luftwaffe budget to match American radio production capabilities. Even then, Germany lacked the raw materials, particularly high-quality quartz crystals and certain rare elements needed for precision components. The conclusion was inescapable. American industrial capacity had made technological superiority militarily decisive. The report reached Berlin on February 25, 1943. It was classified most secret and distributed to only a handful of senior officers in Wehrmacht High Command and the Reich Ministry of Armaments. The response was silence. No new factories were authorized. No crash programs were initiated. The implications were too devastating to acknowledge. But Technical Testing Station 12's work was only beginning. Over the following months, more American equipment fell into German hands. Each capture provided new evidence of American technical and industrial superiority. An SCR-300 radio, the famous backpack walkie-talkie, revealed FM technology, miniaturized into a portable unit that weighed only 18 pounds, yet provided reliable communications up to 5 kilometers. German portable radios of comparable range weighed over 40 pounds and required external battery packs that added another 20 pounds. An SCR-299, captured in Sicily in July 1943, stunned the examination team. This was a mobile long-range communications station installed in a truck with an integrated power generator. The transmitter produced 350 W of power across a frequency range from 2 to 18 MHz. With crystal-controlled stability and the ability to change frequencies in minutes rather than hours. The SCR-299's associated receiver was a helichrydine design with 15 vacuum tubes, multiple conversion stages, and a crystal filter for improved selectivity. German long-range communications equipment of similar capability existed, but only in fixed installations requiring building-sized antenna systems and dedicated power plants. The Americans had packaged equivalent capability in a vehicle that could be driven anywhere and set up in an hour. Each examination revealed the same pattern. American equipment was designed for operation by minimally trained users, mass production by semi-skilled workers, and maintenance by following simple procedures. German equipment required skilled operators, hand assembly by trained technicians, and field repairs by electronics experts. One philosophy scaled to millions of units and global deployment. The other did not. The technical intelligence reports flowing from Tunisia, Sicily, and later Italy documented not just individual radio sets, but an entire communications philosophy. American forces maintained constant contact from squad level to theater command through multiple layers of radio networks. Platoons had SCR-536 handy-talkies. Companies had SCR-300 backpack radios. Battalions had vehicle-mounted SCR-508 and 608 sets. Regiments had SCR-193 and 299 long-range equipment. Each level could communicate with the levels above and below, creating a web of connectivity that German forces could not match. More critically, all American radios used compatible frequency systems and interoperable equipment. A forward observer with an SCR-300 could contact an artillery battalion 20 kilometers away using an SCR-608. Because both used FM on compatible frequencies with crystal-controlled stability. German forces, in contrast, operated multiple incompatible radio systems, each requiring different frequencies, different modulation types, and different operating procedures. By summer 1943, German signals intelligence had documented over 50 different American military radio types, from handheld transceivers to airborne command sets. Production estimates derived from captured serial numbers and intelligence reports suggested that American factories were producing over 100,000 military radio sets monthly. German production, including all services and types, reached approximately 15,000 units monthly at peak capacity. The examination teams began analyzing captured American manufacturing documentation, technical orders, parts lists, and maintenance manuals revealed the infrastructure behind American equipment. Components were standardized across multiple radio types. Vacuum tubes used common base configurations. Crystals followed standard holder designs. Even screws, nuts, and bolts followed unified thread standards that allowed interchangeability. This standardization meant that American factories could shift production between different radio types without retooling. A plant producing SCR 508 transmitters could switch to SCR 608 units by changing only a few fixtures and component types. Parts from one radio type could often be salvaged to repair others. The entire system was designed for flexibility and scale. German manufacturing, in contrast, used custom components for each equipment type. The FUG-5 tank radio shared almost no parts with the FUG-10 aircraft radio. Despite similar electrical functions, each type required dedicated production lines, unique test equipment, and specialized spare parts inventory. Changing production priorities required months of retooling and retraining. Oberg engineer Hermann transferred to a larger technical intelligence facility in northern Italy by autumn 1943. It spent increasing time analyzing American manufacturing methods rather than just equipment design. His reports to Berlin evolved from technical assessments of radio circuits to strategic warnings about industrial capacity. He documented the American electronics industry's explosive growth. Companies with names like Galvan Manufacturing, later called Motorola, had transformed from small radio manufacturers into massive military contractors. Helicopters, a maker of amateur radio equipment, was producing sophisticated military receivers in quantities that exceeded total German radio production. Western Electric, the manufacturing arm of the Bell telephone system, operated factories employing tens of thousands of workers producing crystals, vacuum tubes, and complete radio sets. These companies had not existed as major military suppliers before 1941. The Americans had created an entire military electronics industry in less than 2 years by converting civilian factories, training new workers, and applying mass production techniques refined in automobile and consumer appliance manufacturing. Detroit's automotive engineers had designed radio production lines that operated with the efficiency of car assembly plants. The German radio industry centered in Berlin, Munich, and Hamburg remained organized as it had been in the 1920s. Small manufacturers produced specialized equipment using skilled craftsmen. Production quantities were measured in hundreds per month, not thousands per week. Quality was maintained through individual inspection and hand adjustment, not statistical process control. Automated testing. Hermann's December 1943 report to the Reich Ministry of Armaments was titled The American Radio Industry: An Assessment of Industrial Capacity and Strategic Implications. It documented American electronics production in devastating detail. United States industry was producing annually what would take Germany 20 years to manufacture. The gap was not just technological. It was industrial, organizational, and philosophical. The report estimated that American factories could produce enough military radios to equip 1,000 divisions, though the Americans only fielded approximately 90 divisions. The surplus capacity meant that American forces had unlimited replacement equipment. Damaged radios were not repaired in the field. They were replaced. Outdated models were retired and sent to training units. Newer, better designs were continuously introduced, not as prototypes, but as mass-produced equipment distributed across entire theaters. German forces, meanwhile, carefully husbanded every radio. Field technicians performed repairs under combat conditions, cannibalizing parts from damaged sets to keep others operational. Replacement equipment arrived irregularly, if at all. Newer designs remained in limited production because retooling would reduce output of existing models. The Vemec-operated radios designed in the early 1930s, alongside newer equipment, creating maintenance nightmares and training difficulties. The crystal supply situation was particularly critical. By late 1943, German quartermasters estimated they needed 5 million precision crystals for existing radio equipment and planned upgrades. Domestic production capacity was approximately 200,000 crystals annually. Even if Germany devoted enormous resources to expanding crystal production, it would take over a decade to produce 5 million units. The Americans, according to intelligence estimates, were producing 30 million crystals annually. They had solved the quartz supply problem by finding deposits in Brazil, mining operations in Arkansas, and even synthetic crystal growing experiments. American crystals were not just abundant, they were superior in quality, achieving frequency stabilities that German laboratories could barely measure, let alone manufacture. The examination of captured American test equipment revealed another dimension of the industrial gap. American radio factories used automated test sets that measured frequency, power, output, modulation quality, and sensitivity in seconds. These testers were themselves sophisticated electronic instruments produced in quantities that allowed every assembly line station to have dedicated test equipment. German factories used manual test procedures requiring skilled technicians and minutes per unit. One captured test set, a measurements corporation signal generator, became a prized possession of the technical testing facility. This single instrument, standard equipment in American factories, could generate precisely calibrated signals across the entire radio frequency spectrum. It had cost approximately $300 to manufacture. The equivalent German equipment required a laboratory filled with separate oscillators, attenuators, and frequency meters, costing thousands of rich marks and requiring constant calibration by engineers. By early 1944, the message from technical intelligence was clear and terrifying. American communications superiority was absolute, irreversible, and growing. Every month, American factories produced more radios than Germany had in its entire military inventory. Every captured example showed incremental improvements, design refinements, and manufacturing sophistication that Germany could not match. The introduction of American radar systems in late 1943 and early 1944 drove home the message with even greater force. Radar was in radio. Technology pushed to its ultimate extreme using microwave frequencies, pulse techniques, and sophisticated signal processing. The Americans were mass-producing radar sets for ships, aircraft, and ground installations with the same industrial efficiency they applied to voice radios. A captured SCR-584 fire control radar examined in March 1944 demonstrated technical capabilities that German radar scientists had only theorized about. The set operated on the extremely high frequency of 3000 MHz, used a precision tracking mount with automatic following circuits, and achieved accuracy that allowed anti-aircraft guns to destroy enemy aircraft with devastating effectiveness. The SCR-584 weighed over 10,000 pounds and required a dedicated vehicle for transport. Yet, American factories were producing them by the hundreds. German radar development had focused on longwave systems operating below 1000 MHz because German industry could not manufacture the specialized vacuum tubes needed for higher frequencies. The magnetron tubes used in American microwave radar required precision machining, exotic materials, and manufacturing techniques that Germany did not possess. Even when German scientists designed microwave radar systems on paper, they could not be built because the components simply did not exist in German industry. The systematic examination of captured American equipment continued through 1944. As Allied forces advanced up the Italian peninsula and prepared for the invasion of France, each new example added to the mountain of evidence documenting American technical superiority. Improved radios appeared regularly. The SCR-694, introduced in mid-1944, provided frequency modulation tank communication with increased range and reliability. The SCR-619 aircraft radio offered hundreds of crystal-controlled channels and near-instantaneous frequency switching. Most significantly, American equipment reliability improved continuously. Early production SCR 300 radios had occasional problems with moisture ingress and battery contacts. Captured examples from late 1944 showed redesigned cases, improved seals, and modified circuits that eliminated these issues. The Americans were not just building equipment. They were continuously improving it based on field experience and incorporating lessons learned into ongoing production. German equipment, in contrast, often degraded in quality. As the war progressed, material shortages forced substitution of inferior components. Skilled workers were drafted into combat units, replaced by less experienced personnel. Quality control suffered as factories focused on quantity over reliability. Radios that should have lasted for years began failing after months of service. By the time of the Normandy invasion in June 1944, German technical intelligence had documented the complete picture of American communications superiority. Allied forces landing in France carried more radios than the entire German army possessed. Every Allied company had radio contact with battalion headquarters. Every Allied battalion could reach division command. Artillery. Forward observers directed fire from dozens of kilometers away with perfect accuracy because their radios never lost contact. German commanders attempting to coordinate defenses found their communications breaking down under Allied jamming, artillery fire, and the simple chaos of battle. Radios that worked perfectly on test ranges failed in combat. Crystal oscillators drifted off frequency in the Norman summer heat, making contact between units impossible. Battery-powered sets ran down quickly because replacement batteries were unavailable. The communications network that German doctrine assumed would exist simply ceased to function under combat stress. The technical reports flowing back to Berlin became increasingly desperate in tone. Oberon engineer Hermann, now attached to Wehrmacht operations staff, wrote in August 1944 that Germany had already lost the electronic war. American jamming equipment, direction finding systems, and signal intelligence capabilities allowed the Allies to locate and target any German radio transmission within minutes. German codes were broken, frequencies were monitored, and movements were tracked through radio traffic analysis. The final collapse came in late 1944 and early 1945 as Germany's industrial base disintegrated under Allied bombing. Factories producing radio equipment were priority targets. Telefunken's Berlin facilities were destroyed in November 1944. Lawrence production plants in Stuttgart were bombed repeatedly. The Crystal production facility in Sudetenland fell to Soviet forces in January 1945. By March 1945, German radio production had essentially ceased. Existing equipment continued to function, maintained by increasingly desperate field technicians who cannibalized parts from damaged sets and improvised repairs with whatever materials they could find. Replacement radios simply did not exist. When a headquarters radio failed, commanders lost contact with their units. When tank radios broke down, armored formations became isolated groups of vehicles unable to coordinate action. The Americans, meanwhile, continued improving their equipment even as victory approached. New radios introduced in early 1945 offered enhanced range, additional channels, and improved reliability. Production continued at full capacity, not because more radios were needed, but because the industrial machine could not easily be stopped. By May 1945, American depots were filled with excess radio equipment that would never be used in combat. The end came on May 8, 1945. Germany surrendered unconditionally to Allied forces. Among the items catalogued by occupation authorities were the technical intelligence reports from Tunisia, Sicily, and Italy. These documents, classified most secret by German authorities and hidden in salt mines and underground archives, provided Allied investigators with a unique perspective on their own equipment. American technical teams searching through German facilities in the summer of 1945 were surprised to discover how thoroughly the Germans had examined captured American radios. The reports were accurate, detailed, and professionally done. They correctly identified American technical advantages and honestly assessed German inability to match American capabilities. One report written by Oberon engineer Klaus Hermann in April 1945 as Soviet forces closed on Berlin served as his final testament to the technical war. He wrote that Germany's defeat was inevitable from the moment German engineers opened the first captured American radio in Tunisia. The frequency crystals, automatic circuits, and modular design revealed an industrial philosophy that Germany could never match. The Americans had industrialized warfare itself, applying mass production techniques to every aspect of military equipment. Hermann concluded that future wars would be won not by the side with better soldiers or superior tactics, but by the side with greater industrial capacity to produce high-technology equipment in overwhelming quantities. Germany had excellent soldiers, competent generals, and adequate tactics. What Germany lacked was an industrial base capable of matching American production. This lack was most clearly visible in something as simple as a radio crystal round to precision tolerances by teenage girls in factories that produced millions of units annually, while German laboratories struggled to make thousands. The post-war fate of the German engineers who examined captured American equipment reflected the realities of the New World Order. Klaus Hermann was recruited by American authorities in 1946 and spent 2 years documenting German radio technology for United States intelligence. He later worked as a consultant to American electronics companies, helping them understand and improve upon German innovations that were worth salvaging. Many of his colleagues followed similar paths. The brain drain from Germany to America, formalized in Operation Paperclip and similar programs, transferred thousands of German scientists and engineers to the United States. They brought knowledge of German technology, but more importantly, they learned American industrial methods, mass production techniques, and the organizational philosophy that had made American victory inevitable. In 1952, Hermann published a technical paper in the Institute of Radio Engineers Proceedings titled Comparative Analysis of German and American Military Radio Design Philosophy 1939 to 1945. The paper, based on his wartime experience examining captured American equipment, documented in academic language what he had reported to Wehrmacht High Command nearly a decade earlier. American radio design, he wrote, prioritized ease of manufacture, simplicity of operation, and reliability under all conditions over technical sophistication or component efficiency. German design sought technical excellence, theoretical perfection, and component economy, assuming that skilled operators would compensate for equipment limitations. One philosophy scaled to millions of units and global deployment. The other did not. The paper became required reading in engineering schools and military mize. It influenced a generation of American engineers who designed equipment for the Cold War, the space race, and the computer revolution. The lessons learned from examining German engineers, examining American equipment shaped American aid technological dominance for decades. By the 1980s, many surviving German engineers who had worked in technical intelligence during World War II gathered for reunions and historical conferences. They shared memories, compared notes, and reflected on their experiences. Klaus Hermann, then in his 70s, gave presentations on his work examining captured American radios in Tunisia and Italy. At a conference in Munich in 1986, he displayed photographs of the first SCR 508. His team had examined in February 1943. The images showed young German engineers leaning over the open radio case, measuring circuits, documenting components, and struggling to understand what they were seeing. Hermann told his audience that the moment they removed the first crystal holder and saw 10 precision oscillators installed in a standard tank radio, he knew Germany had already lost the war. The frequency crystal, a small quartz wafer ground to exact dimensions, represented the intersection of physics, engineering, and industrial organization. It was not a complex device in principle. Any competent laboratory could produce one, but to produce millions to a standard quality level with perfect interchangeability at a cost low enough for installation in every military radio required an industrial infrastructure that Germany simply did not possess. That infrastructure created in America between 1941 and 1945 did not dissolve when the war ended. It expanded and evolved, producing transistors, integrated circuits, microprocessors, and eventually the computers and communication systems that defined the modern world. The same companies that had mass-produced radio crystals for Sherman tanks later produced semiconductors for space missions, microchips for personal computers, and the components that enabled global telecommunications. The lessons learned from German engineers examining Americans' equipment in Tunisia became part of the foundation of modern technology. Design for manufacture. Standardize components. Train operators simply build test into the process. Scale production to meet demand. These principles visible in every aspect of American radio equipment in World War II became the standard methodology for all high-technology industries. In 1995, on the 50th anniversary of the war's end, the Smithsonian Institution opened an exhibit titled Communications and Victory, the Radio War in 1939 to 1945. Among the displays was an SCR 508 tank radio, serial number matching the unit examined by Obering Hermann in Tunisia in February 1943. The radio had been recovered from German archives and returned to the United States as part of a cultural exchange program. Beside the radio, the exhibit displayed excerpts from German technical intelligence reports translated into English, documenting the examination process and findings. Visitors could read Hermann's observations about crystal quality, circuit design, and manufacturing sophistication. They could see photographs of German engineers measuring components, testing circuits, and recording data. The exhibit made clear that German technical experts recognized American superiority, reported it accurately to their superiors, and understood its implications. The exhibit also displayed German radio equipment for comparison. A FUG G5 tank radio sat beside the American SCR 508, allowing direct visual comparison. The German radio was larger, heavier, more complex to operate and less capable in every measurable way. It represented excellent engineering constrained by limited industrial capacity. The American radio represented adequate engineering multiplied by unlimited industrial resources. The curator's notes explained that the exhibit was not about praising American technology or denigrating German equipment. Both sides had competent engineers who designed effective equipment within their constraints. The difference was not intelligence, training, or theoretical knowledge. The difference was industrial philosophy and manufacturing capacity. Americans built systems that worked reliably when operated by minimally trained users. Germans built systems that worked brilliantly when operated by highly trained experts. One approach scaled to global war. The other did not. The final display in the exhibit was a small glass case containing a single radio crystal recovered from the SCR 508, examined in Tunisia. The crystal, no larger than a postage stamp, was precisely cut quartz in a hermetically sealed metal holder. The label explained that this crystal, one of 10 installed in a standard American tank radio, represented approximately 40 hours of German skilled labor to duplicate. The Americans had produced over 100 million such crystals during the war, and output that would have required every German radio technician to work for 500 years. The exhibit attracted over 200,000 visitors during its year-long run. Many were veterans who had operated the radio equipment displayed. Some were engineers interested in technology history. A few were historians studying the industrial aspects of warfare. All left with a deeper understanding of how industrial capacity determines military outcomes. Klaus Hermann died in 1997 at age 84. His obituary in the Institute of Electrical and Electronics Engineers Spectrum magazine noted his contributions to radio technology, his work in technical intelligence during World War II, and his post-war career, helping American companies understand German innovations. The obituary also mentioned his lifelong insistence that Germany's defeat was determined not on battlefields but in factories, not by soldiers but by production workers, not through tactical failures but through industrial limitations. His papers donated to the Deutsches Museum in Munich included over 2,000 pages of technical reports, circuit diagrams, component specifications, and strategic assessments written between 1943 and 1945. These documents provided historians with detailed insight into how German technical experts viewed American equipment and what they reported to Wehrmacht High Command. Perhaps the most poignant document in the collection was a personal letter Hermann wrote to his wife in April 1945 as Berlin fell to Soviet forces. He had sent his family to relatives in Bavaria months earlier and remained in Berlin performing final technical assessments until ordered to evacuate. In the letter, he wrote that he was about to destroy all classified documents and equipment to prevent capture. He reflected on the 3 years spent examining American equipment from the first SCR 508 in Tunisia to the latest radar sets captured in the Ardennes. Every example, he wrote, confirmed the same conclusion. America possessed not just better equipment, but a fundamentally different approach to warfare. They had industrialized everything from radio crystals to entire armies, applying the same mass production philosophy that built automobiles and refrigerators. Germany, Hermann wrote, had tried to fight an industrial war with craftsman methods. It was not that German technology was inferior. In many areas, German theoretical knowledge exceeded American. But theory does not win wars. Production capacity wins wars. The side that can build more tanks, more aircraft, more radios, and more everything will eventually overwhelm any opponent, no matter how skilled or brave. He concluded the letter with a prediction. The next war, if it came, would be even more industrial than the last. Victory would go to the nation with the greatest manufacturing capacity, the most advanced technology, and the ability to produce precision components in unlimited quantities. America had demonstrated these capabilities between 1941 and 1945. Any future opponent would need to match or exceed American industrial power, something Herman believed was impossible for any single nation. History proved him correct. The Cold War that followed. World War II became a competition of industrial capacity, technological innovation, and manufacturing capability. The Soviet Union, despite continental resources and massive population, could not match American electronics production, computer technology, or industrial automation. The gap that Herman identified in radio crystals in 1943 expanded to encompass semiconductors, microprocessors, and integrated circuits. The story of German technicians examining captured American radio equipment is ultimately a story about industrial warfare and the revolution in manufacturing that occurred in America during World War II. It is about the transformation of warfare from an activity primarily determined by tactics, training, and courage to one determined by industrial capacity, technological sophistication, and manufacturing efficiency. The frequency crystals that so impressed Herman and his colleagues were not magic. They were precision engineering. Yes, but more importantly, they were precision engineering scaled to mass production. American industry had learned to produce millions of units to identical specifications, something that had never been done before at that scale. This capability developed for radio crystals extended to every aspect of military equipment and eventually to every consumer product America manufactured. The lessons learned by German engineers examining American equipment in Tunisia, Sicily, and Italy were harsh, but clear. Superior individual equipment means nothing if it cannot be produced in quantity. Sophisticated technology is useless if operators cannot reliably use to it. Theoretical mastery is worthless if production cannot achieve it consistently. Manufacturing capacity properly organized and managed outperforms everything else. These lessons, learned at the cost of Germany's defeat, became the foundation of modern industrial philosophy. Design for manufacturability, build in reliability, train operators effectively, maintain equipment properly, scale to demand. The principles evident in American radio hardware during World War II now govern global manufacturing across every sector. Ultimately, the story that began with Obering engineer Klaus Hermann opening a captured radio case in Tunisia in February 1943 concluded with the complete transformation of how nations prepare for and execute warfare. The radio crystal, that small piece of precision-engineered quartz, became a symbol of the Industrial Revolution in military affairs. It marked the moment when victory ceased being determined primarily by battlefield skill and began being determined by factory output. The German engineers who examined American equipment recognized this transformation as it unfolded. Their reports documented not just technical specifications but the end of one kind of warfare and the dawn of another. They observed, analyzed, and reported the future of conflict. That their warnings went unheeded in Berlin did not diminish the accuracy of their evaluations. Today, the principles they highlighted: mass production of precision components, industrial automation, standardization for interchangeability, and design for manufacturability, remain fundamental to every high-tech industry. The direct lineage runs from radio crystals ground in American factories in 1943 to microprocessors manufactured in Asian foundries in the 21st century. The industrial philosophy remains unchanged. Only the scale has evolved. The German technicians who inspected captured American radios in 1943 were not merely studying communications devices. They were witnessing the future of warfare, technology, and industrial organization. Their detailed reports, classified and archived during the war, eventually became historical records that explain not just why Germany lost, but how industrial capacity determines the outcome of modern conflicts. Their conclusion, written in technical language but unmistakable in meaning, was that Germany had challenged the world's greatest industrial power with inadequate manufacturing capability. The radio crystal, a precisely ground quartz oscillator produced by American teenagers in quantities Germany could never match, told the entire story. Industrial warfare demands industrial capacity. Without it, no amount of tactical skill, technological innovation, or personal bravery can achieve victory. That lesson, learned by German engineers studying American radios in underground laboratories across occupied Europe, remains relevant today. In an era of microelectronics, satellite communications, and computer-controlled warfare, the fundamental truth remains unchanged. The side with superior industrial capacity to produce advanced equipment in overwhelming quantities will ultimately prevail. The Americans demonstrated that principle between 1941 and 1945. The world continues to adapt to its implications ever since.